Hello, I'm Ashish Arora. I'm working as a senior scientist at the Molecular and Structural Biology Division of CSIR Central Drug Research Institute, which is at Lucknow. I work in the area of structural biology, specifically in determining the structure of proteins using NMR spectroscopy. Here we have paper 8, Medical Physics, and I present to you module 20, Bloch Formalism and Quantum Mechanical Description of NMR. The objectives of this module is to explain to you what is Bloch formalism, what is the rotating frame transformation, how is the nuclear magnetization detected, what is the continuous wave NMR, and what is pulsed Fourier transform NMR, what is the quantum mechanical NMR spectroscopy. Bulk magnetization is the magnetization as we learnt in the previous module, which is very slight in the z direction and is collinear with the static magnetic field. In NMR spectroscopy, there is a sample of molecules containing spin-half nuclei. This sample is placed in a homogeneous strong static magnetic field. Electromagnetic radiation in the radio frequency range is applied to the sample in a direction that is orthogonal to that of the static magnetic field. The nuclear magnetic resonance absorption occurs when the angular frequency of the applied radio frequency matches the Larmor frequency of precession of nuclear spins. The signal is detected by nuclear induction in a detector coil, which is orthogonal both to the static magnetic field and the transmission coil through which the RF is applied. We will try to understand the theory of this phenomena by using several approaches. The Bloch formalism. Bloch formulated a simple semi-classical vector model to describe the behavior of a sample of non-interacting spin-half nuclei in a static magnetic field. The evolution of the bulk magnetic moment mt, represented as a vector quantity, is central to the Bloch formalism. For a system of spin-half nuclei, the bulk magnetic moment is represented by a vector quantity mt. In the presence of a magnetic field, mt experiences a torque that is equal to the time derivative of the angular momentum. djt by dt is equal to mt cross bt. Multiplying both sides by gamma yields dmt by dt is equal to mt into gamma bt. The physical significance of this equation can be seen by using a frame of reference rotating with respect to the fixed laboratory axis. Let us now consider a frame of reference which is rotating with respect to the fixed laboratory axis with an angular velocity omega of the rotating axis, as you can see in the figure. In the figure, you see that there is a frame, laboratory frame, which is determined by x, y and z, and then there is another frame which is represented by x prime and y prime and having the same z axis, and this second frame is rotating with the angular frequency of omega with respect to the static laboratory frame. So, we have a laboratory frame x, y, z, and we have a rotating frame x prime, y prime and z. Now, we work out the equation of motion in the rotating frame. The equations of motion of mt in the laboratory and rotating frames are related by the equation dmt by dt rotation is equal to dmt by dt lab plus mt cross omega, where omega is the angular velocity, or is it equal to mt cross gamma bt plus omega. The equation of motion for the magnetization in the rotating frame has the same form as in the laboratory frame, provided that the field Bt is replaced by an effective field B effective given by B effective is equal to Bt plus omega by gamma. Now, if we choose omega is equal to minus gamma Bt, then B effective becomes 0, or dmt by dt rotation becomes equal to 0. That is, mt is time independent in the rotating frame, and this has very wonderful implications both from the semi-classical theory and also from the quantum mechanical theory. By inference, as seen from the laboratory frame, mt precesses around Bt with a frequency omega is equal to minus gamma b. For a static field of strength B0 along the z-axis, the bulk magnetization precesses around it with a frequency called the Larmor frequency omega 0, which is given by omega 0 is equal to minus gamma B0. Longitudinal and transverse magnetization. The magnitude of the precessional frequency is identical to the frequency of electromagnetic radiation required to excite transitions between Zeeman level. This identity is the reason that within limits a classical description of NMR spectroscopy is valid for systems of isolated spin half nuclei. Now, here you see that isolated spin half nuclei can be described by a classical model as a rotating spin, but it is such a model would be limited, very limited in its application to isolated spin of half nuclei, whereas most of the compounds, most of the samples, proteins and biological systems that we encounter, they have very differing nuclei in them, and so a different theory has to be developed. Thus, the state of the bulk magnetization in static magnetic field aligned along the z-axis at equilibrium is that there is a net magnetization in the z direction mz. mz precesses at the Larmor frequency around B0, while the magnetization along the x and y axis sum up to 0. The magnetization along the z-axis is called as the longitudinal magnetization, and the magnetization along the x or y axis is called as the transverse magnetization. Now, detection of nuclear spin transitions. We now bring the resonance component for the detection of the nuclear spin. Even though it is precessing around B0, the net magnetization cannot be detected directly because it is collinear with B0. For net magnetization to induce electromotive force in a coil of appropriate geometry, as per the Faraday's law of induction, it has to be perturbed from its collinear position. This is achieved by irradiation of the sample with radio frequency waves of appropriate frequency, such that the oscillating radio frequency magnetic field B1 is orthogonal to the direction of the field and net magnetization. Such an irradiation does not change the precession frequency, it only tilts the rotation axis, and this is very important to understand. Therefore, in another orthogonal coil, the receiver coil, the precession of the net magnetization tilted on its axis induces EMF at a frequency that is identical to Larmor frequency. Continuous wave NMR. Originally, NMR developed through the use of continuous wave NMR spectrometers. In this approach, water-cooled electromagnets were employed to generate the static magnetic field. A probe was inserted between the poles of a cylindrical magnet. The sample was inserted through a holder along the z direction of the laboratory frame. The probe unit consisted of transmitter and receiver coils. Resonance condition was achieved by field sweep method by charging the sweep coils. Another radio frequency channel was introduced for field frequency lock for stabilization of the field, about which we will learn in the next module. An RF oscillator of fixed frequency was used as the frequency source and the signal was appropriately amplified. So, in this case, to achieve resonance, the RF frequency was kept constant and the magnetic field was varied by varying current into sweep coils that were attached to the main electromagnet. The transmitter coil produces the alternating field while the receiver coil serves for detection of the nuclear induction signal. A small amount of coupling between the two coils is admitted to produce a voltage across the receiver coil, and its phase can be adjusted for the observation of either absorption or dispersion. Alternately, an RF bridge system can also be used for detection as done by Edward Purcell. In another variation of continuous wave NMR spectroscopy, the magnetic field was held fixed and the frequency was varied to scan the resonances. So, the techniques to vary frequencies, they came a little later compared to the simple methods of varying the magnetic field. The continuous wave NMR method suffered from several limitations like poor sensitivity, ringing due to relaxation effects, slow repetition rates and limitation to simple 1D NMR experiments. So, it was the early spectrometer that was made by various companies like Varian and Geol, and later it was replaced by Fourier transform or pulsed Fourier transform NMR spectrometers. In the early days of NMR, it was mostly of interest for the physicists, and later when it came to chemistry, then better resolution, better detection was needed, and for which there were further developments in the technique. So, here you see the image of a Geol JNM1 spectrometer and also a schematic for the CW NMR spectrometer. The square poles N and S, as they are labeled, are the poles of an electromagnet, and what you see inside that is a coil, and inside the coil is the sample, and it is also indicated that the sample is spinning. So, there is an RF coil for application of the, this is called as the transmitter coil for application of the frequency, RF frequency, and then there is an RF detector coil and the signal goes to the detector. And these are the kinds of NMR spectrum that were generated. The very first spectrum was generated by Bloch and Purcell. Bloch used water, Purcell used paraffin. CW NMR spectrum for quantitative analysis of tautomeric mixture of 3-methyl-2,4-pentadione was recorded by Jarrett, Sadler and Schulri in 1953. And before that, Dharmati, scientist from India who was working, discovered what is called as the chemical shift, about which we will learn later. And this spectra that was recorded by Jarrett, Sadler and Schulri in 1953 and published in Chem Physics is shown. Now we come to pulsed Fourier transform NMR spectrometer. The pulsed Fourier transform approach, or simply FTNMR, revolutionized the field of NMR spectroscopy. In this technique, the magnetic field was held constant and the radio frequencies sweeping the entire spectral range were applied at once as a burst of an RF pulse of appropriate power. The induced current is measured as a function of time and is referred to as the free induction decay or FID. The The subsequent Fourier transformation of the FID gives the normal NMR spectrum with absorption peaks at resonant frequencies. The simultaneous generation of coherences for multiple spins led to the development of multi-dimensional NMR spectroscopy. This is the FT NMR spectrum of 7-ethoxy-4-methylcoumarin. Schematic representation of the pulsed FT NMR experiment showing top left is a 90-degree pulse detection of time domain FID signal, bottom left the evolution of the density operator through the preparation and evolution periods, and right signal to noise difference between FT-NMR and CW-NMR spectra of 7-ethoxy-4-methylcoumarin for spectra recorded over 500 seconds. This image has been used by Professor Richard R. Ernst in his Nobel lecture given in 1990. The decay of magnetization due to relaxation. So, we are coming back to Bloch formalism after this. At equilibrium, before the application of an RF pulse, the net bulk magnetization is precessing about the static magnetic field B0 with a Larmor frequency of omega 0. This is described by the following equation. dmt by dt is equal to mt cross gamma bt, as we have seen earlier. After an RF pulse has been applied, the magnetization is tilted in the transverse plane and it precesses around the axis of the RF field, which is given as B1. Unless there are some relaxation processes to restore the thermal equilibrium, the transverse magnetization would continue to evolve freely forever. Now, here what we have to see is that B1 is applied orthogonal to B0, which is the static magnetic field. And so, what you see is that the bulk magnetization, which was precessing along the axis of B0, after application of the pulse, now it starts to precess along the axis of B1, provided the resonance condition is met. Bloch defined two relaxation processes that are responsible for the return of the bulk magnetization to the equilibrium state and hence account for the observed decay of the NMR signal. Longitudinal or spin lattice relaxation. The relaxation mechanism known as the longitudinal or spin lattice relaxation accounts for the restoration of the bulk magnetization along the z-axis of its thermal equilibrium state. Bloch's model described the spin lattice relaxation by the first order rate expression dmz by dt is equal to R1 bracket m0 minus mzt bracket closed, such that mzt is equal to m0 minus bracket m0 minus mz0 exponential bracket minus R1t bracket closed, in which R1 is the spin lattice relaxation rate constant and mz0 is the value of the z-axis component of the magnetization at t is equal to 0. The z component or longitudinal magnetization returns to thermal equilibrium in an exponential fashion. The spin lattice relaxation time constant T1 is equal to 1 by R1. Transverse or spin-spin relaxation. In order to account for the decay of the transverse magnetization, which is established in the xy plane after a pulse, Bloch described a transverse or spin-spin relaxation by a first order rate expression dmxt by dt is equal to minus R2 mxt and dmyt by dt is equal to R2 myt, in which R2 is the spin-spin relaxation rate constant and mz0 is equal to mx0 and my0 are the values of the transverse magnetization at t is equal to 0. The spin-spin relaxation time constant is T2 is equal to 1 by R2. So, initially the bulk magnetization is along the z-axis. When we apply what is called as a 90-degree pulse, then it comes into the xy plane and the signal is detected. Now, the magnetization that is in the xy plane has to decay. This magnetization is called as the transverse magnetization, and it decays by following the relaxation rate constant R2, and the magnetization, bulk magnetization, grows back along the z-axis with a relaxation rate constant of R1. Dephasing of coherences. The transverse relaxation process causes dephasing of the coherent transverse magnetization by three main mechanisms. The first process results from magnetic field and RF inhomogeneities. The second process that contributes to dephasing of the transverse magnetization arises from dipolar coupling between spins. The rate constant for this relaxation process is R2 dt. This mechanism of relaxation is sensitive to molecular motion and plays a dominant role in the relaxation of nuclei. The third process that contributes to relaxation is an anisotropic electron density surrounding the nucleus, which is referred to as chemical shift anisotropy. We will learn about chemical shift in a later module. The rate constant for this process is R2 CSA. This relaxation mechanism is important for nuclei in anisotropic bonding environments such as carbon and nitrogen, and is also sensitive to molecular motion. Bloch equations in laboratory frame. The Bloch equations in the laboratory frame are given as follows: dmxt by dt is equal to gamma bracket mt cross btx minus r2 mxt bracket closed. dmyt by dt is equal to gamma mt cross bty minus r2 myt, and dmzt by dt is equal to gamma bracket mt cross bt bracket close z minus r1 bracket mzt minus m0 bracket close. Schematic representation of relaxation process. The spin lattice relaxation in the absence of spin-spin relaxation. Now, as you see in the figure, the magnetic dipoles are indicated and the direction of bulk magnetic moment is also indicated. When the pulse is applied, it is equal to 0, and over a period of time it grows exponentially and comes to its equilibrium value. This is shown in the left part of the figure. In the right part, what you see is spin-spin relaxation in the absence of spin lattice relaxation. So, when the pulse is applied, the magnetization is highest in the transverse plane, and over a period of time this magnetization is lost, it becomes 0. Each panel shows from top to bottom the individual nuclear moments, the bulk magnetization and the Z magnetization mc, or the bulk magnetization in the xy plane, which is given as square root of my square plus mx square as a function of time. Bloch's equations for the rotating frame. In the rotating reference frame, the Bloch's equations are given by dmxt by dt is equal to minus omega myt plus omega 1 sine phi mzt minus r2 mxt. dmyt by dt is equal to omega mxt minus omega 1 cos phi mzt minus r2 myt, and dmzt by dt is equal to omega 1 bracket minus sine phi mxt plus cos phi myt bracket closed minus r1 bracket mzt minus m0 bracket closed. The RF field is described by the amplitude B1 and the phase phi, where omega 1 is equal to gamma B1. and that other omega is an important term and is known as offset. The angle theta through which the effective field is tilted with respect to the z-axis is defined by tan theta is equal to omega 1 divided by omega. Bloch equations for free precession. In the absence of an applied RF field, omega 1 is equal to 0, and the Bloch equations become dmxt by dt is equal to minus omega myt minus r2 mxt, dmyt by dt is equal to omega mxt minus r2 myt, and dmz t by dt is equal to minus r1 bracket mzt minus m0 bracket closed. Evolution in the absence of an applied RF field is referred to as free precession. Let us look at a one pulse NMR experiment and what is called as the superposition of coherent states. In the Bloch model, the maximum NMR signal is detected when the bulk magnetization moment is perpendicular or transverse to the static magnetic field. An RF pulse of duration tau p, strength B1 and tilt angle theta is equal to pi by 2 is applied to the equilibrium magnetization state along the y-axis of rotating frame. So, that phi is equal to pi by 2. The maximum transverse magnetization is generated for a rotation angle alpha of 90 degree or pi by 2 pulse. A 90 degree pulse equalizes the population of the alpha and beta states, and this is what is called as the superposition of coherent state, as is shown in the figure. In the figure, A shows that the magnetization is along the z-axis and the alpha state has a population of n by 2 plus delta n, and the beta state has a population of n by 2 minus delta n. And when a pulse is applied, the bulk magnetization comes along the x-axis and the populations of alpha and beta levels become equal and are equal to n by 2. The one pulse experiment, the complex signal. Following the pulse, a free induction decay signal is recorded for an acquisition period t. The free precession Bloch equation in the rotating frame shows that the free induction decay can be described in terms of two components. mxt is equal to m0 sine alpha cos omega t exponential bracket minus r2t bracket closed, and myt is equal to m0 sine alpha sine omega t exponential bracket minus r2t bracket closed, which can be combined in a complex notation as m plus t is equal to mxt plus I myt is equal to m0 sine alpha exponential bracket I omega t minus r2t bracket closed. This complex signal is detected by the NMR spectrometer as S plus T is equal to gamma m plus T, with gamma being an experimental constant of proportionality. I will repeat. This complex signal is detected by NMR spectrometer as S plus T is equal to lambda m plus T, with lambda being an experimental constant of proportion. The one pulse experiment, Fourier transformation. The complex time domain signal is Fourier transformed to produce the complex frequency domain spectrum. So, S omega is your frequency domain and is obtained by integration from 0 to infinity of the S plus T time domain signal multiplied by exponential bracket minus I omega t dt, and this gives a result V omega plus I u omega. V omega is equal to lambda m0 r2 divided by r2 square plus bracket omega minus omega square, and u omega is equal to gamma m0 omega minus omega divided by r2 square plus omega minus omega square. And this is shown in figure. The top figure you see the FID, which is the time domain signal, and the bottom figure is the Fourier transformed frequency domain signal, which you see in the form of a peak. The function V omega represents a signal with an absorption absorptive Lorentzian line shape, and the function u omega represents a signal with the corresponding dispersive Lorentzian line shape. The real part of the complex spectrum v omega normally is displayed as the NMR spectrum. Quantum mechanical NMR spectroscopy. The state of a spin system at any point during an NMR experiment is described completely by the quantum mechanical representation known as the density matrix formalism. Here let me explain to you that we cannot get directly to understanding the density matrix. There is a very long quantum mechanical explanation explaining the physics and the mathematics, and basically it starts with the Schrodinger equation and then operators, and then it comes to the Liouville space. But then basically fundamentally there is a long set of equations that bring us to the understanding of density matrix, which I am avoiding here and I encourage you to read on your own. In quantum mechanical NMR spectroscopy, the evolution in time of the Hermitian density operator is given by the Liouville von Neumann equation d psi t by dt is equal to minus I h bracket h sigma t bracket closed. The Hamiltonian operator H incorporates the essential physics determining the evolution of the system. If the Hamiltonian is time independent, the solution to the equation is sigma t is equal to exponential I h cross t sigma 0 exponential I h cross t. Quantum mechanical NMR spectroscopy. For a single spin, the state of the system is specified by the density operator, and the density operator is expressed as a linear combination of Cartesian basis operators E by 2, Ix, Iy and Iz. The spin angular momentum operators Ix, Iy and Iz are given by Pauli spin matrices. These operators use the alpha and beta states of the spin as basis functions. The evolution can be followed either through the matrix formalism or through much simpler product operator formalism. The initial state of the spin system is described by the equilibrium density operator, which is given by this equation, sigma is equal to h divided by n kBt and the rest of it. A transformation of the density operator is described as a rotation of an initial density operator sigma 1 to a new operator sigma 2 under the effect of a particular Hamiltonian h. Sigma 2 is equal to exponential bracket I h t bracket closed sigma 1 exponential bracket I h t bracket closed. The effect of a pulse with x phase and a rotation angle alpha applied to Iz is calculated using matrix operation as Rx alpha, Iz, Rx minus alpha, and this comes out to be Iz cos alpha minus Iy sin alpha. If alpha is equal to 90 degree, then Rx pi by 2 Iz Rx minus pi by 2 is equal to minus Iy, because sin 90 is 1 and cos 90 is 0. After the pulse, the minus Iy magnetization evolves under the rotating frame Zeeman Hamiltonian H is equal to gamma Iz during the acquisition period t. So, sigma t is equal to exp minus I omega Iz sigma 0 exp minus I omega Iz or sigma t is equal to Ix sin omega t minus Iy cos omega t. The detectable magnetization is given by Mt, is given by this equation shown here, just too complex to read out, and is equal to n gamma h cross omega 0 divided by 8 kBt exponential bracket I another bracket sigma t omega t minus pi by 2 and closure of both these brackets. Now, the product operator formalism. The product operator formalism works by following the evolution of basis operators under the pulse, which is given by alpha I plus minus x or alpha I plus minus y, and free precession Hamiltonian omega I z. The evolution of basis operations or operators under these Hamiltonians is described. Free precession, and this is very important because normally what we do in a single pulse experiment is that we will apply the pulse, so that whatever magnetization is there, we will treat it with pulse operators and then the system will detect, and during that you have the free precession Hamiltonian. So, Ix in free precession leads to Ix cos omega 1 t plus Iy sin omega 1 t. Iy leads to Iy cos omega 1 t minus Ix sin omega 1 t, and Iz has no change when this free precession Hamiltonian is applied. When the pulse around the x-axis is applied to Ix, there is no change. When it is applied to Iy and alpha I x pulse, then you have Iy cos alpha plus minus Iz sin alpha, and when it is done to Iz, then you have Iz cos alpha minus plus Iy sin alpha. When you apply the pulse along the y axis, then Ix gives you Ix cos alpha minus plus Iz sin alpha, Iy does not change, gives you Iy, and Iz gives you Iz cos alpha plus minus Ix sin alpha. The single quantum coherence term Ix can be expressed as Ix is equal to half bracket I plus plus I minus bracket closed. The trace of this with the observation operator yields this equation, trace exponential IHT Ix exponential IHT f plus, and which is equal to exponential of I omega. This formalism is particularly useful for multi-spin systems, for which it works as a shorthand in place of the rigorous matrix calculations involved in the density matrix formalism. So, with this we have come to the end of this module, and to summarize, Bloch formalism is a semi-classical vector model to describe the time evolution of magnetization. For a static field of strength B0 along the z-axis, the bulk magnetization precesses around it with a frequency called as the Larmor frequency. At equilibrium, the magnetization along the x and y axis sums up to 0. A rotating frame transformation annuls the effect of B0 and makes the magnetization precess in the xy plane. Magnetization is detected by irradiation of the sample with radio frequency waves of appropriate frequency, such that the oscillating RF field B1 is orthogonal to the direction of the main static field and net magnetization. In the earlier days, continuous wave NMR instruments were based on keeping the RF frequency constant and varying the magnetic field with sweep generators. Modern NMR are pulsed FT NMR, in which an intense RF pulse is applied to the sample for a short duration and signal is recorded as an FID. The evolution of magnetization, including the effects of free precession and pulses, can be described by quantum mechanical theory of NMR. Thank you.